It's a beautiful morning. Thank you very much for getting out of your beds and coming here to hear me. My talk is called Carbon Measurement and Attribution for Processes in the Linux Kernel. And I'm very excited to be here. So that's just a bit of brief background. I'm a graduate student and researcher at ETH Zurich. And my research focuses on computer architecture, operating systems, and sustainability. Now, before we start this technical deep dive, just a bit of background so all of us are on the same page, what we're talking about. Now, all of us use computers, right? All of us have these computers in our pocket, and we power them using a number of sources. These sources can include direct DC input or USB or Ethernet, right? You can also power them using batteries, as was the case for these two devices. Or if you're in space, you can power it using energy harvesting. That's also an option. But fundamentally, all devices are restricted by the amount of energy that we can supply to them. A lot of people are saying right now that the amount of computation that we can do is restricted by the amount of energy that we have on the planet. I see some heads nodding. Thank you very much. So if we want to use the maximum, no, we want to use the minimum amount of energy to do the job. Why is that? Why do we want to use the minimum amount of energy? We'll take a look later. So with that out of the way, let's try to focus on the problem. As a developer, as a person who is an expert in DevOps, why would you get a report? How would you implement something that, if you get a feedback that says, oh, your application is terrible, it drains all of my battery. How do you fix it? What immediately comes to your mind? What if your boss asks you to generate the report for the Sustainability Reporting Directive? This kicked in earlier this year, if some of you might be familiar with it. And finally, what if you have a super excited intern who wants to become a crypto millionaire by mining Bitcoin on your servers? How do you find out the guy or the girl? So these are all great use cases for understanding where is the energy in your system going, just to prime our thought process. If I ask you to optimize for performance, you would say, I know this. I've done this before. I will measure the latency or the time that my program uses using well-established tools like perf or time, right? But what comes to your mind when I ask you to optimize for energy? Oops. Yes. Oh, my bad. Right, so think about the tool that comes to your mind when I ask you to optimize for energy. And I would like to pull you all back in history. All of us went to high school, and some of us have really beautiful memories of high school. I want you to pull back one beautiful memory of high school, which is this formula called energy equals power time latency. So you would say, yes, I know this formula, right? I will find out what is the power, and I'll find out what is the latency, and then I'll give you the value, and then everyone will be happy, and we can go home, and we can chill. So I take the power from my CPU. I ask RAPL, hey, tell me how much power you're using. And the CPU says I'm using 15 watts. Great. I use time to measure the amount of time my program takes. And time says, OK, I'm a really great programmer. I take only 5 milliseconds. And I multiply these two values, and I get 75 millijoules, and voila. Are we done here? No, we're not done. It's not that simple. And there are a lot of things that we missed. And I would love to discuss what did we miss, why this is not the right way of looking at things. And that is one of the key takeaways from today's presentation. We need to break out of this mindset what we just saw. This does not reflect what is actually happening in modern systems. So this model assumes that the CPU is running at a constant power. In reality, the CPU power looks something like this. We have a lot of peaks, and we have a lot of valleys. And we need to account for it, right? Otherwise, this data is invisible to us, and that's terrible. The power is not constant over time, and for very good reasons. But as developers, we don't think about this. And it's high time that we break out of this mindset. Second, we focused on the CPU, right? The CPU is the rock star of the system. We love the CPU. However, it turns out that there are other people in the entourage. There's memory, there's network, there's disk. And there's research from Google which says that often memory can dominate the data center server's power consumption more than the CPU. In fact, they optimize for memory's energy consumption more than CPU. And that's really crazy to think about it. Like, Google is optimizing for this at a massive scale. I would love to get more into this because this is a big focus of my research. But in the interest of time and in the interest of audience, let's keep going. So what if I try to do this calculation on different platforms? For example, for ARM, for PowerPC, I cannot. RAPL is restricted only to specific Intel microprocessors. If you say, oh, I'm going to get this value from the data sheet, well, good luck. Data sheets are very often not available, or they're not correct. So we don't have uniform interfaces. We don't have a uniform way to get this data in the first place, right? It's like I'm trying to bake a cake, and every step in the instruction is in a different language. I know that is German, and I know the 5th step is in Spanish, but what about 1, 2, 3? I don't know. So it would be great to develop uniform interfaces. And that brings me to combining of all these 3 problems. We are inaccurately measuring only a fraction of a highly specific system's power, right? And I would like for you to take away the next statement. I love this. I think this is a very important. You can take away as a DevOps mantra, put it on your LinkedIn post. Hey, I learned a new DevOps mantra today. We cannot improve what we cannot measure. It applies to a lot of things in life. We need to measure things correctly to improve them. And that is what my research focuses on. So the goal of my work is to develop a framework or to develop tools and models that help us reliably measure the energy consumption of a process on Linux. But why do we care about this? What am I going to do with this? Like, where am I going with all this? So what is the impact of this work? Why should you care about this work? And for that, I would like to pull you back in history once again. In a very, very faraway land, a long time ago, there was an engineering student. And this student had an exam. And in typical engineering student fashion, he started studying for the exam at just the right time, the night before the exam. And he starts studying, and he's looking at the laptop. I started 30 minutes ago. Why is my battery at 50%? I will not study for the exam. I will find out why is the battery at 50%. And that's what got us here. So the student did not have any tools to understand where is the battery going? What is exactly going on in the system? We don't know. We cannot see. So we want to be able to get this data to the end users in an easy to understand and useful format. But I don't think a lot of us here are users. We are developers, right? We are engineers. We build things. So, and here comes the use case. Your application is terrible. It drains all of my battery. As a programmer, you want actionability. You want APIs that help you see into the fog, where is the energy going? Where is the power going? How do I fix this user's problem that my application is terrible? No, you must be wrong. So we want to do better, okay? And that's what the research focuses on. Now, all right, we understand the problem, we understand the goal. I want to show you the absolutely correct way, like the 100% correct way of doing things. And then we also understand why we don't do that. This is the 100% correct way of doing things. You take a bunch of wires, you put them in your system. It's taking 15.675 watts. OK, but can you do it for this? No, we can't, right? We run on massive server farms. And by the time I finish doing the measurements on all of my servers, yeah, well, I'm not sure if I'll have my job. So we want something that scales. And here's the beauty of software. Software scales, right? Software scales much better than hardware. So we want a software-based solution that scales for this problem. Now, I think we just saw Linux does not have a very reliable solution. Let's take a look at what our contemporaries do. Let's take a look at how other operating systems, if they solve it, how do they solve it? On the screen right now, you see a screenshot from Windows. Windows runs a kernel process known as the energy estimation engine. I did a lot of digging on this, and well, not a lot of details are available. But this process tracks all of your system's per process energy usage, and they report this data to you. If you've been inside Windows Task Manager, or maybe you can even look it up right now, it will show you this data for each application. When it comes to macOS, macOS has a similar process called Power Metrics. You can access this using sudo Power Metrics in your terminal. But in the user-friendly way, you can access this from your activity monitor. the activity monitor has an energy panel which shows you what is the energy impact. Now, this number, I have to be very, very careful here. This number is not a watt or a joules value. This is a meaningless number which allows you to compare. That's it. There are a lot of reasons for this. I would love to discuss more later. But do not take away that this is a joules or a watt number, OK? Android. Android devices are really constrained by energy. So they actually have a proper battery subsystem in the kernel to track all of this. And for iOS, I could not find a lot of data, but I suspect that their service would be very similar to Power Metrics. So all of the contemporary ecosystems and all of the contemporary operating systems have solved it. I have covered the majority of non-Linux devices right here. Why is Linux missing? Any ideas? Well, that's what I'm here to. Yes?
Maybe because it depends on this desktop environment.
Exactly. Exactly. That's a great point. So the question was, why is Linux missing? And he mentioned because it depends on the system. And that is exactly correct. Linux is a very fragmented ecosystem. And that makes the problem much harder to solve. Thank you. I really appreciate that. We'll get to that point later as well. So let's take a look at how some people have tried to solve it in the past. On the screen right now, you see a screenshot from PowerTop. PowerTop is an old tool that came out around 2 or 3 decades ago. I suspect early 2000s. And PowerTop allows you to, oops, are we out of power here? Thank you, Matteo. The forward.
You need to press the white button.
Yes. Yes, thank you. Thank you. OK, so you've run PowerTop. And PowerTop allows you to get the power estimate for a process, a device, or even the display, right? And that's quite interesting when you think about it. However, life is not that simple. It never is. Why is that? Why I do not support PowerTop? Well, there are multiple reasons for that. Number one, power is a discrete time event. I'm sorry for the physics lesson, but we are more interested in energy. Power happens at one point in time, and then that value is never seen again. We are more interested in the energy because that directly affects your battery life. Your battery supplies energy. Second, PowerTop has a vendor-specific implementation. It does not work if you try to use the same tool on other platforms. And third, what is the actionability? And we get back to the question, if I tell you, oops, yes, if I tell you process X takes 1.45 watts, what do you do with this? How do you reduce it? How do you optimize it? We don't know. And we need to know, right? Until we know, until we measure, we cannot improve it. That's why it's very important to have tools which give you depth in this data. And now I'd like to describe a high-level diagram of how I'm trying to solve this. If anyone needs a coffee, now is the time. I'll try to keep it simple. This is a high-level diagram of the system architecture. So on the screen right now, you see this is fundamentally a regression model. We have device-specific measurements. We have the process accounting infrastructure, which combines to give you a multivariate regression. Very fancy jargon. But at the end of the day, I'm just trying to do regression. All you need to do is focus on the equation at the top, AX equal to Y. Really simple, OK? We just take a look at how do X and how do A come through, and we're done with this. First of all, A. What is A? A is the regression parameters. Why do we need the regression parameters? What is the problem? The problem is that the battery tells me how much charge it has left. That's it. So imagine a water tank in which there's just one single input. There's like one big fat pipe, and there's 10,000 small pipes. You want to figure out how much water is going inside each of these 10,000 pipes. And all you can do is you can see the decrease in the water level at point X and point Y. OK? So that is what we're trying to solve. We have one single input, and we want to isolate to all the devices so we can figure out what is the impact of each device on the energy consumption. There's a proper algorithm for this. The first step is to minimize the system load. We get the system to a baseline. We turn off all the devices, whatever we can. We turn off all the non-critical processes. And we get the system in a stable state. At this point, we take a bunch of measurements and figure out what is the baseline load. Next comes the magic. I turn on one single device. I say, OK, if the baseline power is 10, and I will turn on the screen, what is the shift? How much did my power shift when I turn on the screen? And that would be a change that I'm interested in, right? So at this point, I will also sweep the device. What do I mean by sweep? Sweeping means I will turn the screen into maximum brightness. I will turn the screen to minimum brightness, because both of these will have different energy consumption. I will see how much energy at these levels it is using, and then I'll turn it back off. So my system should be back again at baseline. And we repeat these steps for all the target devices. So what we're trying to do once again is figure out what is the water outlet in each of those 10,000 pipes. I'm turning on and off each of these pipes sequentially and figuring out, OK, this pipe consumes X. This one consumes Y. That's all that we're doing, OK? And this allows us to solve for the regression parameters. Next, we take a look at the process accounting infrastructure. So what is the problem here? Well, the problem is a single process is not isolated. A single process uses multiple resources. It uses the CPU. It uses the memory. It uses the disk, file handles, network sockets. And we want to account for all of these. Remember, we want to break out of the mindset that the CPU is the king. No, the CPU is no longer king. Today's systems are very different. So we have one possible process and many possible sources. OK? How do we isolate? Well, here's one more algorithm. Remember, I told you can get coffee. So I'll try to keep it fast. First of all, we figure out the process ID. And we figure out all the group processes in this group. Second, the /proc interface in Linux tracks how much time, how many file handles, how many network sockets each process is using, how many screen wake-ups it causes. We get this data from the proc interface, and we calculate the fraction. Now, why do I care about the fraction? And this is very important. This one took me some time to understand. We care about the fraction because if my process runs for only 5 seconds, and my system runs for 100 seconds, it should cost only 5%. I cannot give the entire 100% value to this small guy who ran for only 5 seconds, right? So we need this fraction really correctly. And once we have the fraction, that becomes our input in the regression model. And no more coffee. We're done with the heavy stuff. Now let's get to the good questions. What are the problems with this? What I would love to discuss with you, what I would love to get feedback on. There are millions of devices, as you pointed out, and billions of ICs inside these devices. The ecosystem is fragmented. And this means that the models can have value ranging from a few milliwatts to actual megawatts. Well, not megawatts, to actual watts. And we need accurate and useful models, right? I cannot have a model that gives you a terrible number. Then we are back to square one. And we don't want that. Second, and this is a classic statement in machine learning community, all models are wrong, but some models can be useful. And I don't know how useful ChatGPT is. We can debate that. But we want to build a useful model. And a useful model is very often a very heavy model. If you use ChatGPT to calculate the energy consumption of your system, I'm not sure that's a great idea, because you're running a super heavy process to do the measurements, right? You're creating load on the system. And that load will skew your measurements. So we want a super efficient, yet a super correct model. That's a very tricky balance to achieve. Third, there's often a significant difference between what we estimate and what is the reality, right? So at the end of the day, this is a machine learning prediction. OK, I just described to you a very fancy machine learning model, which is predicting an energy value. But it is an estimation. It is not the ground truth. We need the ground truth. And we cannot find it, because if I try to go to every server and put my wire into every server, I might not be very happy. So we need to figure out how much is the error margin. What is the error that we see in our measurements? And that's also a bit tricky to figure out. And last but not the least, I need a lot of data. Machine learning models are built on data. Would you be comfortable giving me your energy data? Please. Let me graduate. OK, so we need to figure out a way to collect this data while also preserving privacy. And there's a lot of research which shows that if I know how much energy you're using, I can figure out if you're browsing Facebook or if you're stalking your friends. OK, so with that, we get to this really interesting thing. So we started with carbon emissions, right? It turns out that carbon is mostly dependent on your energy. We talked a lot. We saw so much. How to calculate energy consumption, power times latency. And once you have this value, once you have this single data point, you can calculate carbon super easily. Carbon depends on where you get the energy from. If you're running your system in France, maybe it would be super green. But if you're running your system, I don't know, maybe in the US, you might not get very green results. So the energy mix of the grid determines how much carbon your application emits. And that really brings us to the end product. And remember, I promised to you something that is understandable for our users, something that is actionable, something that is useful for end users, and something that helps a kid pass the engineering exam when they start studying at night. I hope this tool can do that. I hope this simple tool can tell you if a particular application is killing your system and how much. And we're developers, right? Don't forget that we're developers. I hope I can expose these commands. Well, it's already halfway done. I will release it very soon. But a command line API which enables you to get this data in depth and then act upon it. What does it mean to act upon it? It means that when you're writing your code in the IDE, it gives you live suggestions saying, OK, maybe that for loop is not the smartest idea. So live feedback to the developers, which significantly improves their actionability. So all of us can say, yes, I did a great job. And yeah, so it was a lot. I really, really appreciate your attention, but I know that you will not remember everything. If you forget everything, if you don't remember anything, I want you to remember the next two things, OK? If you see me, I don't know, at lunch and say, hey, I remember these two things you told me, I might buy you lunch. The first thing, we cannot improve what we cannot measure. OK? Always remember, this is useful in a lot of places in life. And the second, we need to break out of the mindset. CPU is no longer the rock star. GPUs. There are other guys in the system. Today's systems are really heterogeneous. And until you, the actual people, the actual engineers, question it, it will not change. So please, 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 free lunch ticket. And thank you very much. I really appreciate your attention.